Okay, this chapter's on chapter 6, and I think I mentioned this in the discussion that this is a chapter that contains a lot of different types of calculations, and the best way to go about reviewing and studying this chapter is to do it in chunks of time, so not try to do it all at once, and to make sure you go through each section and can solve the in-chapter problems as you go through. And then as you're reviewing this lecture, I would pause when you need to, since I'll be going through several example problems, and make sure that you can follow those as well. And as always, just make sure you write down any questions that you're having as you go through this and ask them in our class discussion. So the first thing is, the first sort of section here is on balancing chemical equations. So in order to do that, you have to have an understanding of what we mean by writing an equation and what those numbers mean. So if you look at it on a microscopic level, you could say, for this example, that you have 2 molecules of hydrogen gas reacting with 1 molecule of oxygen gas to yield 2 molecules of liquid water. Notice that the phases are written after each, so the gases are written with a symbol G in parentheses, liquids with an L. When we start dealing with aqueous solutions, the symbol there is AQ and S for solid. And when you see an equation, it should have those phases written in. Also recall that hydrogen and oxygen and several other molecules are diatomic molecules when they're on their own in their free state. And so you should be able to take, for example, the statement here, 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to yield 2 molecules of liquid water, and be able to write the equation that you see above. So that relies on the fact that you know which molecules are going to be diatomic, as you see here for hydrogen and oxygen. Something else to mention is that those, because of the law of conservation of mass, we also know that 0.56 kilograms of hydrogen gas react with 4.44 kilograms of oxygen gas to yield 5 kilograms of liquid water. This comes from the law of conservation of mass. This also means that you can use the numbers that are in front, which isn't stated here but is important to know, to represent the number of moles of anything. And I think that'll probably come up later, but it's good to mention now. So another way you could read that equation is 2 moles of hydrogen gas react with 1 mole of oxygen gas to give 2 moles of liquid water. So there are just sort of 2 ways of looking at the equation that are both important and will allow you to solve problems that you're asked. Now, a balanced chemical equation obviously follows the law of conservation of mass, and the number and kind of atoms that you have in a balanced chemical equation have to be the same on both the left and right-hand side of the arrow, meaning on both the reactant and product side of the reaction. That means that the subscripts that you see, so in this example, the chlorine gas, that means there's 2 chlorine atoms there. The subscript 2 means that. And also you need to multiply through any numbers that are in front, those coefficients. So that's how we get that there's 2 sodium atoms and 2 chlorine atoms on the left. And then because that number 2 is multiplied through all of the atoms in a formula, it means there's 2 sodium atoms and 2 chlorine atoms on the right. So this equation is balanced. If we look at an equation like this and think about how we would balance this equation, or think about if it is balanced, again, the numbers get multiplied through. So I'll walk through this one. So on the left here we have 1 mercury atom. If you look at the nitrate, so it's mercuric nitrate there, you'll see that there's 2 nitrate molecules. So that means that 2 gets multiplied through. So that means that there's 2 nitrogen atoms and 2 times 3, 6 oxygen atoms. So the number outside the parentheses gets multiplied through everything inside the parentheses. And we keep following through again, the numbers that are in front get multiplied through as well. So there's 2 potassium atoms, 2 iodine atoms. So that's everything on the left. If we look on the right, we have 1 mercury, we have 2 iodine from that subscript, and then the 2 in front multiplies through, so we have 2 potassium, 2 nitrogen, and 2 times 3, 6 oxygen. one of the more common errors that students make is by adding the 2 and the 3 instead of multiplying. So just pointing that out. Make sure that you're multiplying through the numbers in the front, as well as in that nitrate example, the number outside the parentheses gets multiplied by everything on the inside. And so if we look at this and we see the number and types of atoms on the left and right-hand side, we can see that this equation is balanced. So here's kind of some steps to use to balance chemical equations. I know some of you probably have done this before, and maybe others it's either been a while or you haven't really done a lot of this. So you can kind of figure out which works best for you. But this will give you the stepwise way of doing this. So the first step is writing the unbalanced equation using the correct formula for each reactant and product. Again, this relies on knowing formulas, being able to write formulas from names. So it will rely on your understanding of the previous material we've talked about. Number 2, you find suitable coefficients. Those are the numbers that go in front. Ones are implied but not written. And those numbers multiply through again, and they tell you how many units you have of whatever the number's in front of. And then if you need to, reduce those coefficients. So in this example here, you'll notice that to balance this equation, there's a 2, a 4, a 2, and a 4, and all of those can be divided by 2 to end up with you want the lowest combination of coefficients that are needed. And I always tell students that you want to check your answer when you're done. So when you think that you've balanced the equation, always go through and double check that you have the same number and type of atoms on the left and the right. And if it's been a while since you've done this or you need some extra practice, I would really recommend that you do exactly what you see here and write down the number and type of atoms. So instead of trying to keep track in your head, actually really write it down so that you can see and make sure that you have a balanced chemical equation. Stoichiometry, the word, just means keeping track of sort of the math of chemical reactions. And so we'll talk about some different types of calculations that we can do. A couple of these you've done already. So when we started talking about the periodic table, and we did this molecular weight and formula weight before, so this should look familiar. So the molecular weight is just the sum of all the atomic weights of all the atoms in a molecule. The formula weight is the sum of atomic weights of all atoms in a formula unit, whether it's molecular or ionic. So the distinction here, when you hear molecular weight, is usually that you're referring to a molecule, and formula weight can refer to either. You'll probably hear me actually say molecular weight even when I'm talking about an ionic compound, so try not to let that throw you. I'm just talking about the same thing here. And again, you're taking the individual average masses of each of the atoms and multiplying by the number of atoms you have. So for C2H4, there's 2 carbon atoms. Each carbon atom has a mass of 12 grams. And there's 4 hydrogen atoms. Each has a mass of 1. And so that's where you get the 28 grams per mole. And then HCl, 1 hydrogen atom is 1, and chlorine is 35 or 35.5. So you end up with 36.5. For most of the equations and problems that we'll do, you can use just whole numbers, so 36 would work fine for the calculations that we'll do. So again, you've done those already. You've actually done this type of calculation before too, because we talked about what a formula mass was, and so we know that there's this relationship between a mole of something and the weight of that. And we also know that there's a relationship between a mole of something and the number of molecules or number of atoms, and that being Avogadro's number. So you know these equivalents already, and we'll use them to interconvert as needed, and they will come into play in a lot of the problems that you see in this chapter. So again, as you're thinking about solving these problems, first you want to try to identify what's the information that you're given, what are you being asked for, specifically look at what units are being asked for in your answer, and then think about what equivalents do you have that you could set up to cancel all the units and end up with the correct units in your answer. And that's the approach that I'll use as I talk through most of these problems. So here's the first one. We've solved this type before, but how many moles of ethylene gas are in 15 grams of ethylene gas? You're given the formula here. So you're given 15 grams of ethylene gas and asked moles, and we know that there's a relationship between grams and moles, and that would be the formula weight of ethylene gas. So, and that's a matter of putting the units in the correct places. so that they cancel and leave you with the units that you're looking for. And again, use this approach and you'll always get the right answer. So 15 grams of ethylene gas, so we've got grams on the top there, and we want moles in our answer. So in our equivalents that we're using in the middle, the relationship that we know that we're using in the middle, the formula mass of ethylene is 28 grams per mole. So the 28 grams goes on the bottom so that the grams cancel, and 1 mole goes on the top. And so you'll see that grams on the top cancel with grams on the bottom and leave you with moles in your answer. And in terms of the numbers here, is the 15 divided by 28 gives you 0.536. Again, if you think about setting it up first by using the units and making sure they cancel, then the math is just multiplying or dividing, and you won't inadvertently multiply when you should have divided. So again, use those units to help you with that. Another type of problem, how many grams of HCl are in 0.536 moles of it. So essentially the reverse type of problem. You're given moles and you're asked grams. Again, the relationship here is the formula weight. So moles are on the top here, so we want moles on the bottom. And in our relationship we're using, so the formula mass of HCl is 36.5 grams per mole. So 1 mole goes on the bottom, 36.5 grams goes on the top. Moles on the bottom cancel moles on the top. We're left with grams on the top in our answer. That is what we're asked for. And so then we just multiply the 0.536 by 36.5. Now we can start getting into some stepwise types of problems here now that we know a few things. Now that we know relationships of moles in a formula, we know we know a relationship between grams and moles, and we can also use what's known as a mole ratio, which I'll show in the next, or describe in the next set of problems here. So this is a typical type of stoichiometry problem where you're given an equation and you're asked some information about that equation. So aqueous solutions of sodium hypochlorite, this is bleach, are prepared by reaction of sodium hydroxide with chlorine gas. So again, as you're looking at these equations, it's also important that you're able to write out the equations given the words. So we've got sodium hydroxide and chlorine gas. Chlorine is one of those that's a diatomic when it's in its gaseous free state. And we are preparing that sodium hypochlorite. Actually, in this problem, you wouldn't be able to predict all of the things because you're not given everything as a product. But anyway, the question here, how many grams of sodium hydroxide are needed to react with 25 grams of chlorine? And the first thing you always want to ask when you're looking at these types of problems is the equation balanced? You may be given some where the equation is not balanced first. So you always need to check that first. It should be your first step whenever you're looking at a reaction. So let's look here and see if it is balanced. We have 2 sodium on the left and then 2 sodium on the right. We have 2 oxygen on the left and 2 oxygen on the right. We have 2 hydrogen on the left and 2 hydrogen on the right. So far so good. And 2 chlorine on the left and 2 chlorine on the right. So this equation is balanced. Now you can move forward with the problem that's asked. So they're asking you for grams of sodium hydroxide needed to react with 25 grams of chlorine. We always know a relationship between grams and moles, and it's a good idea to always convert to moles first, and then go back and look and see what other relationships you have that can help you solve this problem. At the bottom here is showing you essentially the 3 steps to take to solve this problem. So the first is taking the 25 grams of chlorine and converting that to moles of chlorine. That's always a good first step. So in these types of problems where you're given grams, convert it to moles as a first step. Then we know a relationship between the moles of chlorine gas and the moles of sodium hydroxide in the balanced chemical equation. So this goes back to the equation itself. That's why it's really important to make sure it's balanced first. So in the equation as written and as balanced, you can see that you have 2 moles of sodium hydroxide that are reacting with 1 mole of chlorine gas. That's what's known as a mole ratio, where you're comparing two things, either reactant and product or two reactants, it doesn't matter. You can compare any two things in a balanced chemical equation to each other and set up a mole ratio. And you can use this to help you solve these problems. Again, using the units and canceling out as needed. So that'll be the second step we do. We'll take the moles of chlorine gas and convert it to moles of sodium hydroxide. Then finally, you can see that the problem asked us for grams of sodium hydroxide. If we have moles of sodium hydroxide, we easily can convert that to grams of sodium hydroxide. So we'll see next all of that worked out. So again, we started with 25 grams of chlorine. We're going to convert to moles of chlorine first. And by the way, you can do these in 3 separate steps if you want, or you can set them up all together as you see here. And it's really up to you as to how you want to do that. So grams are on the top here. We want grams on the bottom. So you can see the 25 grams of chlorine and multiplied by the formula mass there, or set up into that relationship. So 70.9 grams of chlorine is equal to 1 mole of chlorine, and we want the grams on the bottom to cancel. And then at this point we'd have moles of chlorine gas. So if you were canceling out units, you'd see we have moles of chlorine gas. The next thing we want are moles of sodium hydroxide. We use the mole ratio from the equation to figure that out. So there's 2 moles of sodium hydroxide reacting with 1 mole of chlorine. And we set that up so that the units cancel. Notice in the first sort of equivalents that we were using, moles of chlorine are on the top. So we want moles of chlorine on the bottom in the mole ratio. And so that makes moles of sodium hydroxide on the top. So at this point, we have moles of sodium hydroxide. Now if we have moles of sodium hydroxide, we want to convert that to grams of sodium hydroxide. So we use the formula weight. And again, moles of sodium hydroxide are on the top in the middle there. So we want moles of sodium hydroxide on the bottom in the next equivalent. And so the 40 grams of sodium hydroxide, the formula weight, goes on the top. And if you go back and check and cancel out all identical units that you find on the top and the bottom, you will see that you end up with grams of sodium hydroxide as the units in your answer. And that's what you're being asked for in the problem. So in terms of the math here, it's 25 grams divided by 70.9 multiplied by 2 multiplied by 40. And that will give you the 28.2. If you missed any part of this, you might want to sort of go back and review. This mole ratio is probably new for most of you and really important for solving these types of problems. Again, you can set them up in 3 steps, or you can set them up all together as you see here. Another type of calculation we can do is what's known as percent yield, and that's based, it's just a definition of a percent as applied to a chemical reaction. So the actual yield will be the amount that we actually form in a reaction. So oftentimes we don't have 100% yield, so we don't get all of what we could have gotten. And so what we could have gotten is that theoretical yield, the amount that was theoretically possible. So percent yield is just a percent based on that. So the actual yield of product divided by the theoretical yield multiplied by 100% to get it into a percent. There's a couple of example problems in your text that you can look at for this. They're fairly straightforward to give you, the actual yield and theoretical and ask you to calculate that. Or it may be a stoichiometry problem where you can calculate the yield and go from there. But this percent yield is fairly straightforward. Another type of calculation we can do is one that involves something known as a limiting reactant. So we need to understand what we mean by each of those. I should say in the problems that you're going to deal with, you're dealing with just 2 reactants. So when you're looking for a limiting reactant, you have one that's the limiting reactant and one that's the reactant in excess. So for these types of problems, that's what you'll see. The limiting reactant is the one that limits the amount of product that you get. So it's the one that's again limiting how much product you get. Excess reactant, it's the one that you have a lot more of than is needed. You have it in excess. So these types of problems involve similar types of stoichiometry, and then adding on to that this idea of having reactants in different amounts. Okay, so here's an example. We have ethylene oxide reacting with water to form ethylene glycol, and so you can see the reaction there. And they're just giving you more information. I'll skip through that. So we see a reaction. Our first thought then is that reaction balanced? Okay, so I'll get to the question on the bottom that you see here, but the first thing would be, is this equation balanced? So let's sort of go through that. So we have 2 carbon atoms on the left and 2 carbon atoms on the right. We have 4 plus 2, 6 hydrogen atoms on the left and 6 hydrogen atoms on the right. And then we have 2 oxygen atoms on the left and 2 oxygen atoms on the right. So this equation as written is balanced. So we can move on to the question. If 3 moles of ethylene oxide react with 5 moles of water, which reactant is limiting and which reactant is present in excess? So one is limiting, one is going to be in excess. Remember that in a balanced chemical equation, the numbers that are in front tell you the relationship between any two things. That's that mole ratio that I talked about before. So if we look at this reaction, we can see that 1 mole, if we look at the balanced chemical equation, we can see that 1 mole of ethylene oxide reacts with 1 mole of water. So we're going to use that information to help answer this question. This is done in sort of a picture way. I'll sort of talk through in a numbers kind of way here. So if the relationship between ethylene oxide and water is 1 to 1, and in the problem they tell us we have 3 moles of ethylene oxide and 5 moles of water, hopefully you can see that water is in excess here. Because if we had 3 moles of ethylene oxide, we would only need 3 moles of water to react with it, right? Because it's a 1 to 1 mole ratio. So all we would need would be 3 moles of water. So the water is in excess. That means that the ethylene oxide is the limiting reactant. It is limiting how much product we get. So just to follow this through, if we have 3 moles of ethylene oxide and 5 moles of water, and I asked you how many moles, let's see. So ethylene glycol here is the product. Again, that's 1 mole as well. So there's a 1 to 1 to 1 mole ratio. That means that you could predict how much you needed as well, or how much you would get for product on the right. Again, that would be the 3 moles. Usually these types of equation or these types of problems don't give you molar amounts, they give you gram amounts to start, and so you have to do some calculations to answer this. This one you could answer just by kind of thinking about the mole ratio. But the next problem that I'll talk through is more common type of calculation using limiting reactants, and that's this. So we've got lithium oxide used in the space shuttle to remove water, and so they give you the equation here. And again, before even reading any further, the first thing to ask is this equation balanced? So we've got 2 lithium on the left, 2 lithium on the right, 2 oxygen on the left, 2 oxygen on the right, 2 hydrogen on the left, 2 hydrogen on the right. So it's balanced. So the question then asks us, if 80 grams of water are to be removed and 65 grams of lithium oxide are available, which reactant is limiting? And then further questions, how many grams of excess reactant remain, and how many grams of lithium hydroxide are produced? So the first part of this equation gives us a mass of water and a mass of lithium oxide, So again, when you're given grams, first thing that you should do is convert those to moles, and we know a molar ratio here, so we're then going to use that to figure out which one of these we have in excess. Okay, but with limiting amounts of reactant problems, you cannot tell by the mass amounts which one is in excess, just by looking at the masses. So it is not the case that you can just look at this type of problem and say, well, water must be in excess because there's 80 grams of it. That's not true. So in these examples, you always need to convert to moles first. The moles will tell you which you have in excess and which is limiting. So here's how we would set that up. So you want to figure out how much of each you would need to react with the other, essentially. Okay, so they're giving us that we have 65 grams of lithium oxide, okay, in the problem. So if we have 65 grams of lithium oxide, we want to figure out how many moles of lithium oxide is that. So that's the second thing you see there. And then if we have that many moles of lithium oxide, how many moles of water do we need to react with that? Okay, so that's the setup that you see. So we have 65 grams of lithium oxide. We use the formula mass of lithium oxide to convert that to moles of lithium oxide. That's the first conversion factor that you see there. So the grams are on the top in lithium oxide to start, so we want grams of lithium oxide on the bottom in our conversion factor, moles on the top. So at that point you have moles of lithium oxide. Now we want to figure out, if we have that many moles of lithium oxide, how many moles of water do we need to react with that? So we go back to our equation and we see that the mole ratio is that 1 mole of lithium oxide reacts with 1 mole of water. And that's the coefficients in front. Again, the ones are not shown. So that's where you get that 1 mole of water to 1 mole of lithium oxide, is from the balanced chemical equation. And you set it up so that the moles of lithium oxide on the top from before, from the first conversion factor, cancel with the moles of lithium oxide in your second conversion factor. And they leave you with moles of water on the top. And the answer there you see is 2.17 moles of water. So if we have 65 grams of lithium oxide, we would need 2.17 moles of water to react with it. So the next step would be to figure out how many moles of water we actually have. Because if we need 2.17 moles of it, and we figure out whether we have that amount, we have less than that, or we have more than that, that will help us answer what the limiting reactant is. Okay, so we have 2.17 moles of water, so we need to figure out from the mass of water that we're given, how many moles we actually have. So they told us in the problem that we had 80 grams of water. You can see that here, 80 grams of water to be removed. So if we have 80 grams of water, we're going to convert that to moles of water. Straightforward, use the formula weight for water to set up that conversion factor. Grams of water are on the top to start, so grams of water go on the bottom in our factor, and give us 4.44 moles of water. So if we have 4.44 moles actually given to us, but we only need 2.17 moles of water to react with all of the lithium oxide we're given, then the lithium oxide is limiting our reaction. Alternatively, the water is in excess. Okay, so in these cases, one of the reactants is limiting and one is in excess. So we have water in excess here. Lithium oxide is the limiting reactant. You have to identify this first in order to answer the next two questions that you're also asked in the problem. So lithium oxide is limiting. Go back and see what else we're asked here. How many grams of excess reactant remain? So we know that the excess reactant here is water. And so we're going to use just some conversion factors to figure that out. We know that we're given, or we have, 80 grams of water. We know that that's equivalent to 4.44 moles of water. They're actually asking us how many grams of it remain. Okay, so if we want to know how many grams of water remain, we know that we're given 80 grams of it, so we need to figure out how many grams we actually needed and then subtract the 2. So we know we needed 2.17 moles of it. Recall that we figured that out here. So we know that we need 2.17 moles of water to react with the amount of lithium oxide that we're given. So we convert that to grams of water. That's going to be the grams of water that are consumed in the reaction, the grams of water that react with the lithium oxide. So we take the 2.17 moles of water, convert that to grams. Again, the conversion factor is the formula weight. Moles of water are on the top to start, so they go on the bottom in the conversion factor and leave us grams of water on the top in our answer. So we are consuming 39.1 grams of water, yet we're given that in excess. We were actually given 80 grams. So to figure out how much is remaining, we just subtract the 39.1 from the 80. and get 40.9 grams. So that's how many grams of water are remaining, which is the answer to the second question. The third question here asks us how many grams of lithium hydroxide are produced. So we're looking at the product here. Notice in the equation that 1 mole of lithium oxide and 1 mole of water produce 2 moles of lithium hydroxide. So we're going to use that information to figure out how many grams of lithium hydroxide are produced. So we know that, and you actually could take either the water or the lithium oxide here. So either one could be used to calculate this. They're taking the water here. So we know we're reacting 2.17 moles of water. Again, that's the amount that reacts. We have it in excess, but that's the amount that reacts. So 2.17 moles of water, we're going to convert that to moles of product using the mole ratio. So that's the first conversion factor you see there. Moles of water on the top to start, so they're going to go on the bottom in our conversion factor. We use the balanced chemical equation to write that mole ratio. So 1 mole of water is going to produce 2 moles of lithium hydroxide. Again, we get that from the balanced chemical equation, the coefficients that are in front. Again, the ones are not written. Now we have moles of lithium hydroxide, and we need to convert that to grams of lithium hydroxide. We use the formula weight. Moles of lithium hydroxide are on the top in the previous, so we need moles of lithium hydroxide on the bottom, grams on the top, and so that cancels and leaves us grams of lithium hydroxide, which is what the problem is asking us. So 104 grams of lithium hydroxide are produced. So this is the type of problem with limiting amounts of reactants. You can be asked a variety of questions here. Again, you want to think about what's the information that you're given, and you'll notice that in all of these problems that we did or calculations that we did, that mole ratio came into play. Okay, so think about where you need to use that to help you convert from what you're given into what you're asked in the problem. Another type of problems that we can do here are percent composition and using that to derive empirical formulas and molecular formulas. So percent composition just tells you the elements present and gives you a mass percent of each. And you can use that to calculate both empirical formulas and molecular formulas. So an empirical formula tells you the smallest whole number ratio of atoms in a compound. The molecular formula tells you the actual numbers of atoms in a molecule. So it can be either the empirical formula or a multiple of it. And I think I have an example here to show you. Okay, so here's a type of problem that uses this percent composition and asks you about a molecular formula. So we have a liquid that has a composition of 84.1% carbon and 15.9% hydrogen by mass. Determine the empirical formula, and then they're going to give you information in order to determine the molecular formula. So the first step is determining the empirical formula, and so you're going to assume that you have 100 grams of your compound and use that to figure out the number of moles of each thing you have to be able to write the empirical formula, and then I'll talk through how you do the molecular formula. So again, for empirical formula, you're going to assume you have 100 grams of a substance. This is always the case. So where you're given percent mass composition and asked to calculate empirical or molecular formulas, you always assume you have 100 grams of the substance, because then you can use the percents to help you solve the problem. So if we assume we have 100 grams, that means that we have 84.1 grams of carbon and 15.9 grams of hydrogen because of the percent that we're given. Okay, so we were given the percent by mass. So if we assume 100 grams, we know how much is carbon and how much is hydrogen. Now we convert the mass of each of those into moles of them. So if we have 84.1 grams of carbon, we convert that into 7 moles of carbon. Again, using the conversion factor with the formula weight. Moles of hydrogen, we take the 15.9 grams of hydrogen, use the formula weight of hydrogen, we have 15.8 moles of hydrogen. If you use 1, you'd end up with 15.9. So here we have the number of moles of each each type of atom in our formula for carbon and hydrogen. So the next thing to do to figure out the empirical formula is to figure out the smallest whole number ratio that can represent carbon to hydrogen in that compound. And so it depends on what you get for answers here. The way that this is shown, it's sort of 2 steps. Sometimes it just takes 1. But the first thing to do is to take your moles from before. Okay, so we have 7 moles of carbon and 15.8 moles of hydrogen. And we need to figure out what's the smallest ratio of carbon to hydrogen in this compound. The first step is to always divide by the lower number. So you can see here we take the 7 and the 15.8 and divide by 7. That will give you one of them as a 1. Okay? So we end up here with C1H2.26. But 2.26 is not a whole number. They must be represented by whole numbers. So the next thing you do is try to figure out what do you multiply those numbers by to get whole numbers. And again, you have to multiply both of them by that so you maintain the same relationship. Again, this is really just sort of math and working through the ratios in order to get whole number ratios here. So we've got a 1 and a 2.26. So this is a matter of just trying things and see what happens. So multiply them by 2, multiply them by 3, multiply them by 4, etc. until you get whole number ratios. So the example here, what works is 4. So if you multiply each of these numbers by 4, you get C4H9. So that's the smallest whole number ratio that you can get given the percent composition that you were given in the problem. So C4H9. That's then the empirical formula. So go back to the question, and it says, so that's the first part. Assuming the molar mass of this compound is 114.2 grams per mole, determine the molecular formula of this compound. So this is essentially 2 steps. First, you want to figure out if you had C4H9, what would its formula weight be? And that is 57.1. Okay, so that's 4 times 12 for carbon plus 9 times 1 for hydrogen. Sort of not shown here, but that's where they got that 57.1. But you're given in the problem that your molecular mass, the molar mass, that is 114.2 grams per mole. That's greater than 57.1. So what you're trying to figure out here is by what multiple is it greater? And so you take the 114.2, divide by the 57.1, and it's 2. So it's twice as much. So then you just multiply the subscripts by 2. Okay, so you know that you were given a molar mass of 114.2. In order to maintain the same relationship between carbon and hydrogen, that is 4 carbons for every 9 hydrogens in the compound, you multiply each of those by 2 and you end up with C8H18. So here kind of shows you in the calculation what we mean by a difference between a molecular formula and an empirical formula. So the molecular formula will always match the molar mass of the compound. If we took C8H18 and calculated the molar mass, we would get 114.2. The empirical formula is the smallest whole number ratio between the atoms in a compound. So hopefully you can see that C8H18 could be divided by, each of those could be divided by 2, and we would get C4H9. And that would be the smallest whole number ratio that relates carbon to hydrogen in the compound. This type of empirical formula, just to sort of point this out, is very rarely used because it doesn't give us the actual molar mass of the compound, but it does give us a relationship visually sort of the number of carbon atoms to hydrogen atoms in the compound. So hopefully that helps to explain the difference between the two. One way that we can determine empirical formulas is by analysis of the elements. This is sometimes done by combustion analysis, where we burn something in the presence of oxygen, and we produce carbon dioxide and water. So the compound that you're combusting, the hydrocarbon, this is the reaction that you would set up. The hydrocarbon would be sort of the variable here that you were given, or what you were trying to figure out in the formula. The next sort of sections here deal with how we talk about reactants in solution. And a lot of these, or this information relates back to grams and moles, etc., but it's sort of an extension on top of this. The first piece is the definition of something we call molarity, which you may have come across in lab yet, I'm not sure. So the molarity is symbolized with a capital M, and it relates the number of moles dissolved in a liter of solution. So it's equivalent, the equivalent units are moles per liter. And we'll talk a little bit about those types of calculations that you do. In terms of just quick definitions here, so a solution is the mixture that we have, the solute is what's dissolved, and the solvent is what's doing the dissolving. So it's what the solute is dissolved in. So the solute dissolves in a solvent, and that makes a solution. So again, molarity is moles of solute per volume of solution. That's the definition of molarity. Types of calculations here involve obviously moles and volume. And this just shows in the bottom what we would mean by 1 molar. So 1 molar would be 1 mole of solute in 1 liter of solution. So here's some of the types of problems you would do here, and that is figuring out how many grams of a solute you would need to prepare a certain amount of a certain concentration of solution. So that's this problem you're given. How many grams of solute would you use to prepare 1.5 liters of a 0.250 molar glucose solution? So that 0.250 molar is equivalent to 0.250 moles per liter. So we're given 1.5, we need to make 1.5 liters, and we're given a concentration, and we're given that it's of glucose. So one thing to do is to calculate the molar mass of glucose. That's that 180 grams per mole. And just to sort of have that handy, that would be one of those conversion factors that you could use. We're given that we want to make 1.5 liters, and we know that the molarity needs to be 0.250 moles per liter. So we can use that information to convert the liters that we're preparing into the number of moles that we need of glucose. And so that's what you see in the second line down there. So we're given 1.5 liters. The conversion factor here is the actual molarity of the solution. So liters on the top are liters on the bottom in the conversion factor, and moles on the top in the conversion factor. And that factor is the definition of molarity. So we have 0.250 moles for every 1 liter. So that tells us that we need 0.275 moles of glucose to make this solution. If we have 0.275 moles of glucose, we need to figure out how many grams of glucose we need. And so that uses the formula mass. So 0.275 moles of glucose. So moles are on the top. We want moles on the bottom in our conversion factor. We're using the formula mass or molar mass of glucose as the conversion factor here. And we end up with 49.5 grams. So again, it's a combination of the type of problem you've done before in terms of converting grams to moles and vice versa. And now just adding in this definition of what we mean by molarity and using that as another type of conversion factor. Another thing to deal with solutions is using calculations of concentration and volume to figure out. So if you're given a set of concentrations and volumes, to figure out essentially one of the unknowns. Now this, I think, is how your text refers to it. I know this formula is something different, so I'll describe both. So that you're always dealing with initial and final states here. They're showing you the M's as being the molarity, so initial molarity and initial volume, and then final molarity and final volume. I know this equation as V1C1 equals V2C2. It's the same equation, just slightly different in terms of just how you're writing out the variables. So V1 is the volume, C1 is the initial concentration, which is what they call MI. And then V2 is the total volume, and C2 is the final concentration. So in case you've run across it written that way, it's the same formula, just a little bit different. So here's this type of problem. You're given, again, 3 of 4 variables and asked to solve for the third. So we're asked to solve for the unknown. So it's a matter of rearranging the formula so that you can solve for the unknown. So sulfuric acid is purchased at a concentration of 18 molar. How would you prepare 250 milliliters of a 0.5 molar sulfuric acid solution? So we picked this problem apart a little bit. So they're giving you an initial concentration of 18 molar. So that's why you see there the M sub I equals 18. So that's the initial concentration. They're giving you a volume you want to prepare, so that's the final volume. So how would you prepare 250 milliliters? That's the final volume you want to make. So you'll see that's V sub F of a 0.5 molar solution, and that's the final concentration that you want to make, so that's the M sub F. So you're looking for an initial volume. What is the volume that you would use of your initial concentration of 18 molar, and then you would just dilute it up to make that 250 milliliters if you were actually preparing this in the lab. So again, you rearrange the formula to solve for initial volume. You put in the numbers that you have, so the 0.5 molar, the 18 molar times 25 milliliters gives you 6.94 milliliters. And so the way you could word this, you add 6.94 milliliters of the initial concentration to make the 250 milliliters of your solution. We can also talk about stoichiometry in terms of solutions. So we can use, instead of using, say, grams of something, we can use the volume and use the molarity to calculate moles. Again, use the mole ratio as we've done before to convert from moles of one substance to moles of another. And then use the molarity of a second to calculate the volume of solution that we would have. So the only difference here is just we're using volume instead of mass or grams as we did before. So here's that type of problem. So what volume of a 0.250 molar sulfuric acid solution is needed to react with 50 milliliters of a 0.1 molar sodium hydroxide solution? Again, as in all cases, you want to look at your equation and ask if it's balanced. I'm just giving you a little time to check that. So we see, yes, in fact, it's balanced, and we can move forward with solving the problem. And so below that is giving you kind of the outline of steps we'll take. We're given a volume of solution of sodium hydroxide, that 0.10 molar. So we're given the volume of it and the concentration. We can use that to figure out how many moles we have of sodium hydroxide. And then once we know the moles of sodium hydroxide, we can use the balanced chemical equation to convert that to moles of sulfuric acid. So you can see here we've got 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid. So that's the mole ratio that we'll use to convert from one to the other. And then we'll have moles of sulfuric acid, and they're asking for volume. So we'll use the molarity that we're given to figure out the volume that we need. So again, the moles of sodium hydroxide we have available, we take, just to sort of back up here, they give us 50 milliliters of a 0.1 molar solution of sodium hydroxide. So that's the information we'll use to start. So we have 50 milliliters of sodium hydroxide, and the concentration is 0.1 moles per liter. That's just from the definition of what we mean by 0.1 molar. And then another thing that's important here is that you need to make sure that your units are all in the same, that they're in the same units. So you'll notice we have milliliters of sodium hydroxide to start, but liters in our conversion factor. So either convert the liters to milliliters to start with, or as they've done here, do it as part of your your second step. So that's why you see that 1 liter and 1,000 milliliters there. You have to make sure that you've arranged your problem to set all of your units to be equivalent to each other. So you can see here that liters on the top cancel with liters on the bottom, and then milliliters on the top cancel with milliliters on the bottom, and leave us with moles on the top. So the 50 moles of sodium hydroxide is equivalent to 0.005 moles of sodium hydroxide. Again, we're using the volume that they give us and the concentration to figure out how many moles we have. If we have 0.005 moles of sodium hydroxide, we're going to use the mole ratio. That's the next thing down below. We know that we need 1 mole of sulfuric acid will react with 2 moles of sodium hydroxide. So we arrange that conversion factor for the moles of sodium hydroxide to cancel. And we know that we have a concentration of of sulfuric acid of 0.25 molar. And we know that because that's what they gave us. So what volume of 0.25 molar sulfuric acid? So we use that we're given as the second conversion that you see there. So that will convert the moles of sulfuric acid into the volume. And again, we need to factor back in to calculate into milliliters. So that's the third conversion factor that you see there. And so we end up with 10 milliliters of that solution. And they actually didn't ask for the volume in this particular problem in milliliters, although it's given that. So you could have done this and reported it in liters. So you could have said it was 0.01 liters of that sulfuric acid. Depends on how the question is being asked. Okay, the last sort of section here is titration. I'm not actually going to go through the process of titration, but to just show you one of the problems that's related to it, because I know you're going to do titration in the lab. And that's as shown here. So this is really just applying stoichiometry to a reaction. So we have 48.6 milliliters of a 0.1 molar sodium hydroxide solution, is needed to react with 20 milliliters of an unknown hydrochloric acid concentration. What's the concentration of the hydrochloric acid solution? So again, we're using volumes, molarity, and mole ratio to figure out this problem. So we're given a volume of sodium hydroxide, and we're given a molarity of it. So the volume of sodium hydroxide can be converted into moles of sodium hydroxide. Once we have moles of sodium hydroxide, we can use the mole ratio in our balanced chemical equation to convert that to moles of hydrochloric acid. Notice the relationship here is 1 to 1. And then once we have moles of hydrochloric acid, we can use the volume they give us, 20 milliliters, to calculate what the molarity of hydrochloric acid is. If this is helpful, sort of writing it out as you see below here, obviously do that if it helps you in terms of sort of visualizing the steps involved in the process here. For some folks, it's easier to just sort of write out the units and do it that way, so whichever works best for you. So again, here's the problem. We're given that we have 48.6 milliliters of sodium hydroxide, and the molarity is 0.1. So we use that to figure out how many moles of sodium hydroxide that is equal to. So you get 0.00486 moles. We take the moles of sodium hydroxide and figure out how many moles of HCl would react with it. It's a 1-to-1 relationship, so you can see here that 0.00486 moles of sodium hydroxide are going to react with 0.00486 moles of HCl. Now we know moles of HCl, and we can use the volume that we're given to calculate the molarity. So that's the last part. We have 0.00486 moles of HCl, and we're going to divide that by the volume, because again, molarity is moles per liter, and we're going to correct for that milliliter, is going to correct that to liters. So again, just a double check by units, the moles on the top stay in our answer, as they should, and the milliliters on the top cancel with milliliters on the bottom, and they leave us with moles per liter in our answer, and that's the same thing as molarity. And so we end up with 0.243 molar HCl. You could also say that that was 0.243 moles per liter of HCl. And we'll stop there.